Unless something gets added later, we'll wrap up our review of the mathematical underpinnings for the course with a look at number bases. Several of the problems that we're going to look at over the semester will be much easier to solve if you can leverage how our positional numbering system works. Therefore, let's review those fundamentals along with an example of how we can exploit it. First off, we'll see that a multi-digit number is really just a shorthand notation for a math equation. If we have a particular base b, which for our purposes will always be a natural number greater than 1, the number that we see is just a string of symbols drawn from an alphabet consisting of b distinct symbols. Each one of those symbols represents a value somewhere between 0 and b minus 1. So in our decimal number system, we have the digits 0 through 9. If we index the symbols, what we call digits, starting from the right-hand side, and we also start our indexing with 0, we come up with the very simple equation for how to convert the symbols in that string to the value they represent. We simply sum up across all the digits the value of that particular digit, d sub I, multiplied by the weight associated with that digit's position in the string, which is b raised to the ith power. Some examples using three different number bases are shown here along with their base 10 equivalents. Note that the use of the subscript to indicate the number base. Whether this is used depends on whether or not the context makes it sufficiently clear what the number base happens to be. To make sure that we understand the distinction between a string, which is what we're going to be working with in this course, and the value represented by that string, let's take a look at a simple example in explicit detail. We have S, which is a string of symbols, in this case consisting of the characters 4, 8, and 6. To make this clear that this is a string, we'll surround it in double quotes. We'll seldom do this in the course, but in this example we need to make a clear distinction between what is a string and what is a value. Let's assume that we have a function that takes a string as an argument and returns the value that that string represents. Here we will call that function val. In C, this function is a to I, standing for ASCII to integer. Most languages have similar functions. Here, when we pass it our string s, the return value is 486. Notice the lack of quotes, since this is an actual value. Now let's write our string as the concatenation of two strings, x and d, where d is the last symbol in the string. In this case, d is 6, and x is the prefix leading up to it, namely 48. Both x and d are just strings, and each of them has a value that they represent in what other number base we happen to be working with. If b is equal to 10, which is just our ordinary everyday decimal number system, then the value 486 can be written as 48 times 10 plus 6. We can link these two values to the strings that represent them using our val function. The result is that the value s, the value of the string s, is the value of string x multiplied by the number base, and the result is then added to the value of the final symbol. This is the relationship that we're going to leverage. Let's say that we want to find the residue of the value represented by string s, which we will indicate by the variable r sub s. If possible, we would like to be able to read the string s one symbol at a time and have the result available upon processing the final symbol. Using the string s from the prior slide, the value we want for r sub s when we are done is 486 reduced modulo n. We can use the relationships we've previously established to come up with the final equation shown here. Pause the video and take as much time as needed to satisfy yourself that each step is correct and makes sense. This equation is the key to how we're going to process our string, because it tells us that if we simply track the residue of the string up through the first k symbols, that the residue of the string consisting of the first k plus 1 symbols is simply the residue of the prefix multiplied by the base and then added to the value of the k plus first symbol, the whole result then being reduced modulo n. At this point, we're ready to proceed to the next symbol. Upon reaching the final symbol, we have the residue of the entire string. So how do we start? When we read the first symbol, we need to have the residue of its prefix, which is the empty string. In order to make the math work out correctly, we merely define the residue of the empty string to be 0. Let's walk through this procedure by hand, or possibly just in our head, to determine the residue of this relatively large number expressed in base 7 when reduced modulo 5. First, let's recall our trusty formula, and then let's walk from one symbol to the next. One of the first things we can do in this particular example is reduce the value of the base, 7, modulo 5, to get a coefficient of 2, since 7 and 2 are congruent in a mod 5 world. We then start out with setting our residue equal to 0, that's the residue of the empty string. Now we multiply the current residue by 2 and add 4, reducing the result mod 5 to get 4. You can walk through the rest of the steps, pausing the video if needed, to get the result that, after processing the last symbol, the result of the starting value is 3. We can confirm this by converting the original value to base 10, and then using the well-known rules when dividing by 5 in base 10, we can see that by inspection that the residue is indeed 3.